Good afternoon, everyone, and welcome to our WebEx. Kevin Sargison here with Balluff Canada. Going to be joined shortly by Jason Diaz and Greg Soden. So all three of us will be walking through this traceability part 2 presentation. This is solutions in LF, which is low frequency, and HF, which is high frequency. So that's going to be the topic of our discussion today. So please feel free to send us any questions you may have electronically, and we will do a question and answer period at the end, as we always do. So what we're going to begin looking at today is just the different technologies that Balluff plays in. So if you look at the left-hand side of your screen, what you will see is the V-series processor at the far left of your screen. Then the processor in the center with the two heads attached to it is our traditional BIS or ID processor, and then at the right is the I/O link. So that's what we're going to be focusing on today, both in low frequency and high frequency.
Before we get started on looking at high frequency and low frequency, I want to talk about some of the components that make up an RFID system. Just to begin with, we'll talk about the data carrier itself. The data carrier is what holds memory. In our case, Balluff has passive data carriers, and we'll go through in a little bit what a passive data carrier is and what an active data carrier is. Other terms for data carriers could be a code tag or just a tag, but it is the device that holds the memory. A read-write head serves the function of powering that data carrier, as well as reading and writing data to that data carrier. And that connects to a processor. The processor serves as a main controller and a buffer for the memory. It sends commands back and forth from an outside source, and that would be either a controller, either a PLC or a PC type of controller. The processor will integrate into that controller using various bus systems. It could go serial or Ethernet TCP/IP if it was a PC application, or various industrial protocols like DeviceNet, Ethernet IP, Profibus, Profinet, EtherCAT if it's an industrial PLC. So again, the processor itself, you can see there are various form factors that a processor comes in. And the processor itself receives and initiates commands from a controller. That controller, again, being a PC or PLC, it will receive commands and initiate commands. It's connected to a read-write head, and therefore it causes that read-write head to read and write data to a data carrier or a tag. Some processors come with an integrated antenna. So what that means is it has an integrated read-write head. It doesn't require an external one. Other processors come with external ports where antennas get connected. The processor converts data from the tag to a common interface. And again, that interface can be one of those various protocols we talked about. At the bottom, we've given you a partial list of either serial or parallel, interbus, Ethernet. There's, again, Ethernet IP, which is one of the most common ones here in North America. There's DeviceNet and EtherCAT. We have pretty much every protocol covered when we're talking about an industrial or PC application. The antenna, also known as a read-write head, it serves the function to receive and transmit commands and power. And it in turn powers and activates those passive tags, those code tags. It does that over an air gap, and every tag and head combination will have a different range. When we get into the tags, we'll talk a little bit more about range and what influences the range of a tag. The head reads and writes data to compatible RFID tags within a field zone. So again, if you take a look at our catalog, you'll see the various combinations of read-write heads and tags and the field zones associated to each one of those. The size of the antenna is in direct relation to the reading range or the reading area. And this again, if you think about an inductive prox, it really works the same way. The larger the prox, the more range it's going to have. The antennas here work the same way as well. The larger the antenna, the more range it's going to have. The antennas, or let's call it the RFID heads, also have various antenna designs, and there are two designs that Balluff uses. The first one's called a rod-style antenna, Again, if you take a look at our catalog, you'll see how some antennas are labeled or classified as rod-style antennas. A rod-style antenna typically has a longer range, but it is directional. Every read-write head or tag that we have that has a rod-style antenna will have a directional arrow, and that tells you in what direction it could travel. It's ideal for dynamic operations and longer operating ranges. The other antenna that we use is called a round antenna. A round antenna does not have quite the range that a rod-style antenna does. However, the benefit of this is that it is not directional. It can pass in any direction. One important thing to point out is you cannot mix and match these. If you have a tag, a data carrier, which also has an antenna, if that data carrier has a rod-style antenna, the read-write head would also have to have the same rod-style antenna for it to work. You cannot mix and match between the two types of antennas. Today we're talking about high-frequency and low-frequency RFID systems. Both of these types of systems use a technology known as inductive coupling. And I want to bring that up today because I just want you to understand the differences between what inductive coupling is and what backscatter technology is, which is what UHF technology will use. Inductive coupling is very similar to a transformer, where you pass power over an air gap, and power, in this case, an RFID tag. Both sides, the read-write head and the RFID tag, have coils. So the energy is transmitted over, it powers the tag, and it uses pulse modulation to transfer data. The benefit of inductive coupling is it is more resistant to environments such as being mounted on metal and other environmental influences like water or liquids. It is not as influenced as backscatter technology. Typically, if you take a look at an antenna that's using inductive coupling, all these antennas will have a coil winding to it, so it looks exactly like a coil. Backscatter technology, spread spectrum backscatter technology, is used in UHF types of applications. This technology is like a pinging system. It sends out a command, a pinging command, and it looks for responses back from as many tags that are out in its field. That's very different from inductive coupling technology, where you're talking about one tag and one read-write head. In backscatter technology, we're talking about one read-write head or one antenna and multiple tags that can respond when it's in its field. This is what's used in UHF technology. We'll cover UHF more in our next session next month.
So Jason just covered our inductive coupling and backscatter technology. So inductive coupling, as Jason mentioned, really covers our low frequency and high frequency tags, and the backscatter is our UHF technology. So let's have a quick look at what the comparisons are between the two. With inductive coupling and backscatter, in both cases, the RFID head sends out power and information and receives information from the tag or the data carrier. With respect to the inductive coupler or the inductive coupling, where the low frequency, high frequency tags, you're typically having a read area range in either millimeters or centimeters, whereas with UHF technology, or the backscatter, is typically measured in meters of distance between the head and the tag. With inductive coupling, your frequency range is typically under 100 megahertz, and of course with the UHF is over that amount. So Jason just covered the inductive coupling technology, where he used the analogy of a transformer, which we see here. And with the backscatter technology, the analogy would be comparing it to a flashlight. So you can see that the range kind of spreads out like a cone and has a much longer distance. Now with the inductive coupling style, the area of range in which it's able to communicate is consistent. So it doesn't matter where the tag is positioned within that coverage area, it will always read and write data to and from the tag. Whereas with the spread spectrum backscatter, within that range, there will be areas that have holes where there will not be the ability to read and write consistently within that range. So as we move forward in the next session, it'll become apparent that it's important for us to do proper analysis of those applications when doing so. So if you wanted to have an analogy between the two, they're showing the difference between a solid block of cheddar cheese for the inductive coupling style, whereas in the backscatter would be comparable to like a piece of Swiss cheese. There's areas that it can read and areas that it will be, there'll be holes. So let's look at the environmental effects of RFID technology in general. There are some media where the RF signal will travel through certain types of media, such as wood, fibers, plastics, cardboards, paper, that kind of thing. So in that case, we're able to transfer read and write data to and from through those pieces of media. Now there's other types of materials, such as liquids, where the RF signal is absorbed by the liquid. So the RF signal is not able to travel through liquid. On the other hand, with metals, it's actually the opposite. Instead of absorbing it, it acts as a reflector. So RF is not able to transfer through metal. They're actually reflected. So we need to be careful in understanding the environment in which we're implementing RFID technology. So what's a data carrier? So a data carrier also is referred to as an RFID tag. And you have essentially three components that make up a tag. You have the substrate material, which we see illustrated in two examples. And on that substrate, there's an IC chip, an integrated circuit chip. And connected to that, there is an antenna. So that through your read-write head, you're able to reflect or transmit data to and from the tag. There are different types where we can read only data from the tag, or there's others where we can write and read data to and from the tag. You'll see, if you have the opportunity to look through our RFID catalog, you'll see that there are many, many different sizes and form factors of RFID tags, which are dependent on the application. So the reading range and writing range is dependent on a couple of different factors. The type of tag, so are we using a inductive coupling type of tag or the backscatter type technology, which is of course related to the operating frequency, the working environment, so is it surrounded with a lot of metal, for example, and the type of tag, so the size of the tag and the antenna size of the tag. I think that was a point that Jason mentioned a little bit earlier, is the read-write distance will be dependent on the type of tag that you use and the type of antenna. So again, RFID tag and data carrier are one and the same. So how do tags differ? There are a few different types, and what you'll find is that with Balluff, we use passive tag technology, which is the inductive coupling type. And that's where we do not require the use of a battery. There are also battery-assisted passive tags and active tags where there are batteries used, and that's one thing that you don't have to worry with Balluff. Memory type, we have a read-only tag that is in our BISC series, and we have worm technology, so it's write once, read many in our BISL. So you may have a customer that wants data, very specific data put in the tag. We can offer that service where we write that data to the tag, but once it's written to that RFID tag, it's done. You can't change it. Then of course we have where we're able to read and write to all series of tags. So this gives you an idea of the operating frequency. ranges. In our low frequency and high frequency tags, it's using the inductive coupling technology, and then we move up into the backscatter type technology that they're referring to as electromagnetic coupling, and you can see the operating frequencies of our UHF tags, and above that is the microwave tags. So again, we've been speaking a little bit about passive tags or passive data carriers. This is where there's no power supply or battery that's on the tag itself. The tag does not initiate communication. It only does so when the tag and the read-write head become within range. And all Balluff tags are passive. So we have two basic types, the inductive coupling for our low frequency and high frequency tags, and there you can see the different families, the BISC, BL, M, and V series tags. Underneath that would be our UHF tags, or the electromagnetic backscatter coupling technology, and that's referred to as the BISU family. So there's a few different types of memory technologies. E2PROM or EEPROM, that's electrically erasable, programmable, read-only memory, where there's no battery. The tag will retain the data for a period of 10 years, and you're limited to 100,000 writes to the same memory area of the tag. That's our BISM. Then we have the ferroelectrical random access memory, referred to as FRAM. It's very similar, but there's no battery like the above. The same thing for the retention of the data is 10 years. But here you have an unlimited amount of read-write cycles to the same memory area of the RFID tag. So it's important to check the type of tag that you require for your application. Low frequency tags, looking at some of the characteristics, it operates at 125 kilohertz. This is important, is that your read-write range is between 0 to 100 millimeter range. And you have RFID tag memory sizes from 192 byte up to 8 kilobyte. In the BISL family, this will be your most cost-effective option. Typically, though, for low memory requirements, but gives you the most cost-advantage, cost-effective solution. It's very robust, so it's well-suited in high metal type environments. You have both read-only and read-write tags available, and you're able to communicate onto all the common bus networks that Jason mentioned earlier at the beginning of our session, as well as I/O link options. Typically, your applications involve production control, so that would be for like air-proofing type applications, assembly lines, for example, if you're doing linear manufacturing of, let's say, seating systems, and tool ID, so for CNC type applications. For high frequency, of course, it's at a higher frequency than the low frequency tags. It's operating at 13.56 megahertz. But now you have a range up to 400 millimeter read-write range, and you'll notice that your memory size is higher, up to 32 kilobyte. The speed in which you're able to read and write to the carrier has been increased. You have high memory options with the FRAM. There's also high temperature tags that are available depending on what your customer's application is. Again, you have a full selection of bus interfaces. You're able to have both read and write options, and there's a whole variety of different form factors of the RFID heads. This is where we're investing the most. You'll see this technology, especially in the M series. We're growing that side of our business. The other feature is that we're able to do dynamic reading. So this is where the tag can travel past the read-write head on the fly. As long as it's within the proper speed, we can read and write data to and from the tag on the fly. So as far as applications, similar, we can do production control, life cycle management. So if we're looking at the life cycle of a tool, intralogistics, so if we're tracking parts within a facility, anti-counterfeiting, so we want to make sure that the customer is putting the right part into a piece of capital equipment to avoid catastrophic failure. Tool ID, similar as for low-frequency RF and assembly line applications.
Thanks, Greg. Now we're going to continue with what's in the BIS-V product family, or a little detail on the BIS-V product family. This is the next generation processor, so you'll note this looks more like our BNI type of modules. If you're familiar with our Ethernet IP or our IO Link type of modules, this carries basically the same type of form factor. It features the ability to have 4 antennas. They can be low frequency or high frequency. Generally, you don't want to mix high and low into one module. It also has an IO Link master port, so you can run IO Link IO off of this BIS-V master, and it has a built-in Ethernet switch for daisy chaining. So there you see on your right-hand side of your screen, you see a picture of the module itself, and you can see where the connections are for your Ethernet and where you would plug in your read-write heads, your aux power, etc., and where your IO Link, if you choose to use the IO Link capability, where the IO Link block would plug into. And the connectivity is also shown there. So it has the same connectivity that we have with our other devices: Profinet, EtherCAT, Ethernet IP, Profibus, and CC-Link. Now the V processor uses special heads. You can't use a standard BIS-L or BIS-M or BIS-C head with the V processor. So you have a specialized head that you have to use, and this picture shows the different types of heads that are available. They will always have a VM code if they are a BIS-M type of head, or you can also use the L system, the BIS-L. So all those readers will have, or antennas will have, an L in the part number. That signifies they are an L head and able to use an L tag. One of the biggest things you'll notice with the BIS-V is the higher memory and higher speed capacity that this processor has. So the key thing here is the storage capacity now goes up to 128 kbytes. We were limited to 32 bytes in the past. The unit is also 8 times faster than ISO standard 15693. You don't really need to know that standard, but what you need to know is that the unit is much faster. We have practically unlimited read-write cycles. Our transmission frequency is at 13.56 megahertz. And again, we have the capability of 4 read-write heads with 1 processor. You can see down at the bottom, we have different types of heads available. So you have your round antenna, which Jason described with what the round antenna would look like earlier in the presentation, and related tags. And next you have the rod antenna and the related tags. So again, you want to make sure that you're using the correct tag with the correct reader or antenna. You can't mix and match. One of the big features is speed and the amount of data that you can write to the tag. So what we have here, the chart shows you down at the bottom the read-write times of our new VM head, our VIM processor, with the ISO 15693, I believe it was, that we showed you earlier. So the blue dotted line shows you the ISO speed standard, so 25 seconds to write 64 kilobytes. And if you look at the green colored line that's labeled write, we can do 64 kilobytes in about 5 seconds. So much, much higher speed, much higher throughput. The handheld programmer, many of you have seen this before. The handheld programmer is an industrial built device. It has different software options, either the template software or the portal software. It is WLAN and barcode options available. It is a Windows CE based device. So if you have a product that is scattered around a manufacturing facility, you can take the handheld and just scan the tag and read the data right there from the tag. Now, we mentioned earlier you can have an IO-Link interface with the BIS-M. So we had the traditional 10-byte IO-Link with version 1.1. We now have a 32-byte capacity with IO-Link version 1.1. What this means is more memory capability and quicker response time as well. You can see the difference down at the bottom with the minimum cycle time at 8.8 milliseconds versus 24 milliseconds. And you can see the 10 input byte capacity, and now we have the 32 input bytes, 32 output byte capacity. So it allows you to put more data on the tag. There's also an 8-byte IO-Link version 1.1, which is a read-only. So you're just basically looking for the license plate or a number on the tag. We also offer with the BIS-M some long-range capability. You can see from the picture we can go up to 432 millimeters. So we have various antennas that allow us to get the longer sensing range, and of course the tag is also going to be larger. But we just want to make sure you understand we have the capability in high frequency. Subnet 16 is a low-cost RFID network solution where one processor can control up to 16 read-write heads. So this is a way to be more cost-effective when multiple read-write heads are needed. We can also offer high-temperature tags in both high frequency and UHF. UHF we're going to get into more in the next presentation, but we have high-temperature tags rated at 220 degrees Celsius for applications that demand high temperature.
All right, thanks, Kevin. So just to sum everything up, the technology that we have talked about today is low frequency and high frequency. Low frequency is available in our BIS-C systems, BIS-L systems, along with the BIS-V system. If you recall the BIS-V system, you do have the ability to connect a low frequency BIS-VL heads. In this type of system, in the low frequency system, we have read-only options as well as read-write options. If you take that in comparison to the high frequency, you'll see that there are no read-only options. Memory sizes for the low frequency system are 192 bytes at the low end and 8K at the high end. And then for the high frequency system, this is where our BIS-M and BIS-V come into play. They both operate at 13.56 megahertz. They also conform to various ISO standards. They have read-write capability as well as a memory size of starting at 112 bytes up to 128 kilobytes. So quite a bit of capacity there in terms of memory. And then if you compare range, the low frequency systems had a range of a maximum of 100 millimeters. Keep in mind though, the lower the frequency, the better or more resistant it is to environmental conditions like being mounted on metal. So it is better for harsher environments as long as the read-write range does not have to be too far away. Whereas the BIS-M or V, the high-frequency solutions, they can go up to 400 millimeters away. They can still handle harsh environments. We do have tags that can go on metal on the high-frequency side, so we do still have options for our customers. And that was it for today's presentation. We will now open the floor and turn the phones on for questions.
Yeah, we've got one question here. The question is, can I mount tags directly onto metal?
All right, Jay, I can take that one if you want me to. The first answer is, the easiest answer is no, you cannot mount tags directly on metal, but you can if you follow the correct mounting procedures. So there's, in the back of our catalog, you'll notice there's, if you go to the back section, the technical section of the catalog, you'll find that there's spacing requirements and mounting requirements which allow you to mount a tag on metal, providing that you have a metal-free zone around the tag. And the parameters are all defined by the type of tags that you're using. We also do offer a metal mount tag in the BIS-M family that can be directly mounted on metal without having any free zones around the metal. So it's kind of a yes-no question. It's something that you have to pay particular interest to, and you have to ask the question to your customer, what will you be mounting the tag on? Very imperative that you ask that question.
Yep, we've got one other question here. Can I read and write L-series and M-series tags with the same processor and antenna?
I'll take that one there, and I think we did mention that our new BISV system is able to connect to LF, or low frequency antennas, as well as high frequency antennas. It is important though to understand that even though you can do that, tags and antennas must match. So a low frequency tag has to be read by a low frequency antenna, and vice versa. And M, which is our high frequency antennas, they can only read the M or high frequency tags. So you cannot mix and match those.
One other question is for data transfer. Is IO-Link as fast as the BISV series?
I'll take that one as well. IO-Link is not meant to be a super fast, high data capacity system. IO-Link is more for smaller amounts of data being transferred, and by small I mean 32 bytes to about 64 bytes, and that's bytes total. It's probably meant for areas of that capacity. It works really well for read-only types of applications. However, if you're going to get into high memory, we're talking in the K, so 1K, 2K kilobyte range, and you're moving a lot of data at one time, you definitely want to go with the BISV, something that's much faster to handle that kind of data.
Take that as a no. There's no more questions. Okay, thank you very much for your time, everyone.